potential energy, electric potential energy, electric potential. That's what we want to talk about. So I'm going to talk about a ball. Suppose I take this ball and drop it. How fast is it going when it hits the ground? So this is a problem you've already done. So let's say I have this. It starts at height h above the ground. It has a mass m, which I don't really care about. And I want to know how fast it's going right down here. You could use Newton's second law. You could use the momentum principle. But since I don't care about time, I'm going to use the work energy principle. I'm going to go fast because I don't want to talk about this. So the work energy principle says work is a change in energy. If I include the Earth and the ball as my system, then I have two types of energy. I have three terms. I have the kinetic energy of the Earth, I have the kinetic energy of the ball, and I have the gravitational potential energy of the Earth ball system. But there's no external forces on that system, so there's no work done. So I would say 0 is the change in kinetic energy of the ball, which the Earth, let's say, doesn't move, plus the change in gravitational potential energy of the ball. And then I can solve for these situations. So let's call that 1. Let's call that 2. I have 0 equals K2 minus K1 plus U2 minus U1. And if I release it from rest, K1 is 0. So 0 equals K2. And let's just put this as delta U. And 0 equals K2 plus mg delta Y. Since it's moving down, it decreases in gravitational potential energy. And if it moves the distance h, I could say this as 0 equals K2 minus mgh. So by decreasing in gravitational potential energy, it increases in kinetic energy, and everything's happy. And you could solve for the velocity, which I won't do. Okay, now suppose I have a different situation. Note here that there is a constant downward gravitational force. It's important. Now suppose I have a constant electric field and I have a positive charge. And I'm going to let it move in this constant electric field and it will speed up. It has a constant force on it, so it's going to keep speeding up, and I could calculate how fast it's going using the same ideas as before. And in fact, if you look this way and you turn your head, it's the same problem that we just did. It just uses the electric field and electric charge instead of the gravitational field and the mass. So I'm going to have work, change in kinetic, plus change in potential energy. But here, it's not gravitational potential energy. It's electric potential energy. So in this case, delta U is going to be equal to negative E, well, let's call it delta S, times Q. That is the change in electric potential energy. For a constant field, this is only for constant. Okay, so you have to be very careful about that. If the electric field changes, this doesn't work. Okay, so where does that come from? If we have a system and we have work done by some force, in this case we'd have work done by the electric field, and it doesn't depend on the path you take, you can make that a potential energy. And that's how we get this. It's the same thing we did with gravitational potential energy. So that's the definition of electric potential energy for a constant field. Now, we have another thing that we like to think about. We like to think about delta V. And this is the change in electric potential. Okay, so this is the change in potential energy. We just call this the change in potential in units of volts. And delta V equals delta U divided by Q. So if I remove that charge, and I just want to look at the space here, what's the change in energy per unit charge? That's the voltage. Well, we call it voltage because units are volts, but it's really the change in electric potential. And so for a constant electric field, delta V is negative E delta S. So if you're moving in the same direction as the electric field, then you have a decrease in electric potential. If I move in the opposite direction of the electric field, then I have an increase in electric potential. Just like with the gravitational field. If I move the ball up against the gravitational field, then that's an increase in gravitational potential energy, and then this would be a decrease. Okay, so that is the electric potential. And just so you know, I mean, it's not a constant field, but if you look at this D-cell battery, and it says the voltage is 1.5 volts, and then I measure that voltage, if I measure that with a multimeter like this, that is the change in electric potential. What you're measuring is the change in electric potential. So it's a pretty big deal when we talk about circuits. So you do need to think about this. Okay, let's think about the other very important thing. What if I have a point charge and it creates an electric field, and I want to find the change in electric potential around that point charge? That's the other thing that we need to think about. Okay, so let's suppose that we have that. I should have a story to tell when I'm erasing the board, but you just gotta wait. Okay, so first let's think about, here's a positive point charge, and we have an electric field around it that looks like this. And as you get further away from that charge, the electric field decreases. So before we said the electric field, if I have some point right here, and this is the vector R, the electric field is K, Q, R hat over the magnitude of R squared. And so I talked about this before. K is the Coulomb constant, 9 times 10 to the 9th Newton meters squared per Coulomb squared. And then R hat is just a unit vector, but this gives you the unit vector electric field. Now, what if I want to find the change in electric potential? If I start over here and I move towards the charge, then I can't use that equation. I can't say the electric change in potential is negative E d delta S, because the electric field is not constant. As I move closer and closer, the electric field gets greater and greater. So it's a hard problem. And in fact, you're not really going to solve this problem because it involves calculus. But we did something like this with the gravitational potential energy due to a planet. It looks the same. So if I start from an infinite distance away and move in to a distance r, then I can find the change in electric potential. So we say delta V, and I'll put over here, with respect to infinity, is K, Q over R. So this assumes that V at infinity is equal to 0. So we set that. We say, when you're an infinite distance away, the electric potential is 0. And then when you move up to this distance r, it's KQ over R. Because really potential doesn't matter. It's always changes in potential, because it's related to the potential energy, and work deals with changes in energy and changes in electric potential energy. So this is just a convention that we use. We say it's 0 at infinity, and then we can cheat and just talk about the potential at R. Okay, but it's always a change. In this case, we're just dealing with infinity. Now, this is important, because let's make a plot of this. If this is potential as a function of R, it's going to look, we have 1 over K is constant, Q is constant. We have 1 over R, so it looks like this. Now, I want to make a really important point here. What happens to the electric field What's the relationship between electric field and electric potential? So the change, if I look at my earlier definition for constant electric field, negative delta, I'm going to write it like this, delta E. I wrote that wrong. Sorry. I'm going to write this as E equals negative delta V over delta S. This looks like the slope of the voltage position curve, the negative of it. Okay. So if I look right here, the slope is this line, and the negative of that, that's a negative slope, but this would be a positive electric field. Okay. But the point I'm trying to make here is that don't think just because it's a large potential, it's a large electric field. That's true in this case. But what if I have a case like this? We can actually have situations like this. This is maybe the electric potential due to two particles. Down here, the electric field is 0, but the electric potential is not, right? Because the slope here is 0. So don't think just because the electric field's 0, the potential's 0. Or just because the potential's 0, the electric field's 0. Those are different things. One other very important thing about the electric potential. Look at this equation right here. Vector, vector. Not a vector, not a vector, not a vector, not a vector. Electric potential is not a vector. That's good, right? Because now if I want to find the electric potential due to two charges, it's not so bad. Let's say I have a positive charge right here and a negative charge right there, and I want to find the potential here. I can find the potential due to this charge plus the potential due to that charge and add it up. I don't have to worry about direction because potential is not a vector. Okay, so that's enough to get you started with electric potential.